Welcome you to this webinar, and today's presentation is a far-field view of ocean acidification in the South Atlantic Bight. This series is hosted by the Southeastern Ocean and Coastal Acidification Network, and it lays the foundation for the state of ocean acidification science in the Southeast regions and conversations associated about that. They are intended to create a dialogue among scientists and other stakeholders to identify what we know about ocean acidification in this region and what we don't know, and what research in other regions of the United States can be applied to better understand ocean acidification and its impacts in our southeastern region. With awareness of and access to this research and its application and uses, webinar participants will be able to collaborate, and we hope to better understand and adapt to ocean acidification moving forward. Again, my name is Paula Keener, and I'm a member of SOCAN, and I'll be facilitating today's session. We also have Jennifer Bennett-Mintz. She is the Education and Outreach Coordinator for NOAA's Ocean Acidification Program. She's joining us online, and she'll be helping to answer any questions from the attendees. During today's presentations, attendees will be in listen-only mode. You are welcome to type questions related to technical issues or questions that you have about the presentation to the presenter into the questions box in the bottom of the control panel on the right-hand side of your screen. We will be monitoring these incoming questions and will respond to them or pose them to our speaker after the presentation. We are also recording this session, and the video of the recording and the PDF of the presentation will be available on the SOCAN website shortly after the presentation. We are very excited to have Rik Wanninkhof join us today. Rik is an oceanographer at NOAA's Atlantic Oceanographic and Atmospheric Laboratory in Miami, Florida. He's been there since 1991, and Rik is also an adjunct professor of the Rosenstiel School of Marine and Atmospheric Science at the University of Miami. And Rik's specialty concentrates on the grand geophysical experiment studying the effect of increase of carbon dioxide in the atmosphere on the ocean. And the emphasis is on quantifying the transfer and mixing of carbon dioxide in ocean basins and impacts on the geochemical cycling in the ocean. Much of Rik's efforts focus on sustained observations of the anthropogenic uptake of CO2 and the effect of rising CO2 levels on the ocean biogeochemical cycles and the ecology. Rik has a strong interest in improving process understanding of biogeochemical cycling through field studies and interpretation. And he's contributing to national and international syntheses efforts, assessments, and program development. Rik plays a leading role in the implementation and synthesis of results of 3 major projects funded by the Climate Observation Divisions of NOAA's Climate Program Office and the NOAA Ocean Acidification Program. And these projects focus on executions of NOAA's strategic planning, elements of the climate adaptation and mitigation, and healthy oceans objectives. And the following major projects executed by the Ocean Carbon Group at AOML under Rik's guidance include the ocean carbon dioxide sources and sinks, looking at surface water CO2 measurements from ships of opportunity. Secondly, the Global Repeat Hydrographic CO2 Tracer Survey, and then third, the Oceanic, Coastal, and Estuarine Ocean Acidification Observing Networks in the North Atlantic, the East, and Gulf of Mexico. Rik has received numerous awards and recognitions, most recently the Aslo John Martin Award. He's received a Department of Commerce Silver Group Medal Award, as well as a Group Gold Medal Award, the NOAA Administrators Award, and he has written over 160 scientific publications. So please join me in welcoming Rik Wanninkhof. Rik, I'm going to turn it over to you to move forward with the presentation. Okay, Rik, you should have control of the screen now.
All right, I Hope that you can hear me. I will go into presentation mode now. Yes, welcome everybody. First of all, thanks to Paula for the very nice introduction. It was almost a talk in itself, and also to Jen to help us getting along and for organizing this, what I hope will be an exciting seminar series. And I also like to thank many of you who are on the SOCAN committee. I think this is a really valuable effort to make the connection to of ocean acidification to sort of regional issues. I also must mention that this is, okay, the webinar is working well so far for us here. Webinars are very strange in that you are talking to a screen and you don't have any audience reaction. So I've got an audience of one here in the office. Letitia Barbaro is with me, and hopefully she'll keep things going and keep me from straying too far afield. So the title of the presentation that I'll be giving is a far-field view of ocean acidification in the South Atlantic Bight, kind of showing my interest in global ocean work and how this connects to local ocean acidification effects. Okay. So this presentation will be sort of loosely built around a hypothesis that the transient variability in physics and chemistry have a larger impact on ocean acidification in the South Atlantic Bight than current models suggest. And also work you through this hypothesis, and you know, you'd like to have hypothesis proved to be true, and I'll give it away. I believe that this is a correct hypothesis. What I'll do in the next 30 minutes or so is spend quite a bit of time on actually the issue of ocean acidification and explaining what ocean acidification is, or at least what I believe it is, how it impacts ocean chemistry, how it impacts the inorganic carbon chemistry, which I have a specialty in, and then the connection to the global carbon problem. So this is sort of a long and general introduction, but I think it will be useful for the audience. And then I'll look at ocean acidification in the South Atlantic Bight and beyond. Again, looking at the far-field effects on the South Atlantic Bight, and it will be largely descriptive, looking at spatial and temporal patterns, and putting these changes in context of the large-scale oceanographic features. And I expect that you'll get a lot of really good presentations in this seminar series from a lot of experts in this area, and I've listed some. And so I'm using some of their data and some of their insights, but I don't want to give too much away from, I think, some of the exciting work that they can present. To start out is ocean acidification suffers but also benefits from a general knowledge in the public about what acidity and pH is. And the advantage is that people are not completely, dumbfounded when they hear the terms, but it also often leads to misconceptions about acidification, ocean acidification. And over the weekend I was Googling pH scales and came across this, I think, fairly remarkable site about best of raw foods, where they obviously pH is an important thing, where they stated, very simply put, the pH scale measures the amount of oxygen in your blood. This is very simply wrong. Also, what's very interesting in this site is that are obviously, acidification researchers and acid persons, and hopefully they're not one and the same, but acid person is obviously somebody with low energy and no enthusiasm. So I don't think that characterizes us very well. But it gives you sort of an idea of that we are sort of having, the general public has a overall knowledge what acidity and pHs mean, but they don't have the concepts quite right. This is one of the things that we're trying to do in ocean acidification research is make the link to the socioeconomic issues that result from ocean acidification. And this is a paper that I think most of you probably have looked at in the last couple of weeks from Ekstrom et al. In Nature Geoscience, where they basically are trying to make the link between ocean acidification and vulnerability and adaptation of U.S. shellfish industries. So this is shellfish industries by itself, but we see a very sort of two interesting things. I have highlighted the South Atlantic Bight region, and what you can see is that based on this analysis, it is the threat of ocean acidification to the South Atlantic Bight is fairly low, indicated by the gray area, but the social impact or vulnerability is really high. And so this is a sort of an interesting issue. Also, if you look at the other regions, it's an interesting perspective is that there's a very little correlation, at least in this study, between the social vulnerability and degree of severity of OA. And the point that I'm going to make in this presentation is that if we have the social, or if we have the OA threat incorrect in this region, we are probably in a lot more problems with social vulnerability than this particular analysis indicates. Now let's, since we've seen sort of incorrect interpretation of acidification, let's just go to the definitions of ocean acidification as we can find in several program documents, and in this case, actually the federal act that is providing research funds for ocean acidification research in the U.S., which is called the FORM Act, the Federal Ocean Acidification Research and Monitoring Act. And in this act, they define ocean acidification as a decrease in the Earth's ocean and change in ocean chemistry caused by chemical inputs from the atmosphere. I've sort of italicized that. And they mention including carbon dioxide, and I would state primarily carbon dioxide. So the physical chemical driver of ocean acidification is atmospheric CO2. And a significant part of this atmospheric CO2 which is increasing due to burning of fossil fuels entering the ocean. And so this is this term that Paula mentioned is the grand geophysical experiment. We are in a unique situation that mankind is perturbing the chemical balance in the ocean in a significant manner. To sort of illustrate ocean acidification pathways and sort of the challenges to define and research ocean acidification, I've made this graph, and it ended up not working out quite as well. It's still a work in progress, but I'll work you through it to give you some sort of an idea of what's, how, at least in my mind, ocean acidification works. So the primary driver, as you saw in the FORM Act language, is chemical constituent in the atmosphere entering the ocean. In this case, the primary one is carbon dioxide that enters the ocean and then reacts with the inorganic carbon system with the ocean, and basically has a direct effect on the ocean calcifiers primarily, and then it can cascade through the the higher level ecosystems. This is a fairly straightforward, effect which we understand, at least the forcing part, which is on the left-hand side, we understand reasonably well. We need to monitor it to be able to be sure that we indeed have the understanding and to be able to do decent projections. But then we get what I call the confounding effects, is that we have actually a minuscule amount of carbon dioxide entering the ocean each year, going into an ocean which is chock full of inorganic carbon. And so this inorganic carbon cycle, or the natural carbon cycle, has a large effect on the air-sea-CO2 exchange and the surface water pH levels. And when we have this combination of increased CO2 into the ocean affecting the natural variability, we get feedbacks and amplification, which again has a major effect on ocean acidification. And so you basically have a natural cycle, which I have the green arrow, impacting the ocean ecosystems, and then we have the red arrow, which is the ocean acidification impacts. Then there are other issues. There is variability of other chemical parameters, both natural variability and anthropogenic input. And here I make an example of the issue of eutrophication and hypoxia in the ocean. This can interact directly with the ocean carbon cycle as well and cause phenomena which are impacting the carbon chemistry of the surface ocean. I call these compounding effects, and from an ocean acidification perspective, I believe this is a secondary role. Its primary role is actually the actual effect itself, like eutrophication or hypoxia. Then also the biology itself can have a feedback on the impacts, and thinking of phenomena like harmful algae blooms. Again, the biological impacts, the natural ones, are significantly greater than ocean acidification. But it gives you sort of an idea of how you have sort of direct effects and then compounding and indirect effects affecting the ocean acidification, which makes the problem and also sort of explaining the problem challenging. So if we're studying the forcing of ocean acidification, I talk about forcing and then the response, and this presentation is exclusively about the forcing. You can't avoid having a little bit of chemistry, and I'm a chemistry major as an undergraduate, so I like to do a little bit of explaining of the chemistry involved. I'll try to go through it pretty fast because I've been told that not everybody has the same joy of looking at chemical equations that I have. But we really have three species of interest in ocean acidification research. It is the partial pressure of CO2, that's the CO2 which comes from the atmosphere into the ocean. When it gets in the ocean, it's actually a very small component of what we call the inorganic carbon content of the ocean. It's less than 1%. Then, when we think of ocean acidification, we automatically think of the acidification scale, the pH, which is a negative log of hydrogen concentration. And the interesting part is that there is very, very little, very few hydrogen ion concentrations in the ocean compared to the other inorganic carbon species. And then, which I'll go through in a minute, is one of the primary drivers or impacts on ocean biota, particularly the calcifying organisms, is the carbonate ion. And I'll basically, most of my presentation will be discussing the carbonate ion or its derivative, which I'll explain in a minute. They are all related through chemical equations, and the first one is basically the equation when the CO2 in the air basically goes into the water. Then you have a reaction with water, and you basically form a bicarbonate, and there you have your hydrogen ion. But this hydrogen ion basically reacts almost immediately with the carbonate ion. And so what the major effect of ocean acidification is, in particularly with regards to calcifying organisms like shellfish, is that you're decreasing the carbonate ion. And you can make a net equation where you can leave the hydrogen ion out altogether, which is shown in the last. Now, for this presentation, we are going to go one step further and not talk about the carbonate ion, but actually a saturation state, which is a chemical. It's a calculated parameter which basically says the state of the mineral, in this case the aragonite mineral, which is a calcium carbonate mineral, which is important in shell building. And the definition is basically that the aragonite saturation state, or omega AR is the chemical formula, is product of the carbonate ion, the calcium, and the solubility, and it ends up, I'll show in a minute, it's the carbonate ion that has a determining influence on the saturation state. From a chemist's point of view, it's important to remember is that if your saturation state is less than 1, the mineral phase will dissolve. If it's more than 1, it has a tendency to precipitate. The important thing from ocean acidification perspective is that while this chemical balance or threshold of 1 is critical, it is actually any decreases, most of the research has shown that any decrease in aragonite saturation state will cause calcifying organisms to be stressed. So we like to talk about thresholds in ocean acidification, but there are thresholds, but a lot of it is it's a sliding scale that less, and lower saturation state will cause increasing stress on organisms, which will cascade through the food chain. The discussion will be largely, since I'm giving the presentation to the CCAN audience, will be on South Atlantic Bight, but I'll put it in context of one of a series of cruises that we're undertaking on about 5-year timescales, which have been called the Gulf of Mexico East Coast Carbon Cruises. We did the second one several years ago. And this gives you an idea of sort of the realm, and I'll place the saturation states in the South Atlantic in context with the this whole area which we study. Now let's start out with some chemistry in graphs to give you some sort of a feel of how the different species which I just described are related. First of all, and this is using, again, the data of the Gulf of Mexico East Coast cruise. The first plot is we're showing all the data for the cruises from top to bottom. We went, from basically the surface as deep as 4,000 meters. And the first plot to the left shows the correlation between the partial pressure of CO2. We express it sometimes as a viscosity. It's for all intents and purposes the same. So it's a partial pressure of CO2 versus the pH. And we see a very, very strong correlation between the two, which is a more important thing to remember, is that the CO2 and pH are very, very closely related. And on the right-hand side, to make it even better, if we get away from this crazy minus log scale and just plot it into concentrations, we can see that the partial pressure of CO2 is linear related to the hydrogen ion concentration. Now, I should stress that much of the ocean acidification story is really in the width of this line. There is a lot of information which is in the variation of this line, but in large scales, we can say that the FCO2 and the hydrogen ion concentration are strongly correlated and linear correlated. Now, I mentioned that the species of interest is a carbonate ion or the aragonite saturation state. So what I've done here is for all the GOMEC 1,500 data points or so of stations taken during GOMEC 2, I plotted the partial pressure of CO2 versus on the left-hand side the carbonate ion, and on the right-hand side versus saturation state. And there are a couple of things you should sort of jump out at you. One is that, again, the FCO2 or the partial pressure of CO2 has a large influence on the carbonate ion concentration, but it's not nearly as tight as the hydrogen, and also that the carbonate ion concentration and the aragonite saturation state look very, very similar. For those of you who think that it is that the top line that looks very tight correlation is surface water and the bottom is down deep, that is not quite correct. On the right-hand side, basically show the data which is in the top 20 meters of the GOMEC realm, and you can see that it does not follow that top line. But it is worth remembering is that if you compare these two lines, it is that the carbonate ion concentration and the aragonite saturation are very closely correlated. The little appendices you see at the partial pressure of around 800 are basically, it's the effect of pressure on the aragonite saturation state. So that's where the differences are. So these are all deep waters, and the aragonite saturation state is dependent on pressure. Now, this was sort of a quick run-through of the chemistry of ocean acidification, and let me step back for a minute and kind of look at where we're going to with ocean acidification entitled "What Will the Future Hold?" We cannot study ocean acidification without looking at the atmosphere, because that's where essentially the ultimate driver is. And what I've done here is I've plotted the atmospheric CO2 concentration since 1900, which is based on indirect observations since 1958. We have direct observations in Mauna Loa and now at about 80 stations around the world. And so I've sort of plotted in my projected lifespan, my current life and my projected one, and I'm optimistic that I'll live over 100. But what I want to emphasize here is that we are basically at the start of a very, very rapid change. We are seeing changes already. In the last 50 years, we've seen a change in atmospheric CO2 concentration, which will directly affect the surface water concentrations of about 90 parts per million. In the next 50 years, we expect a change close to 300 parts per million. It will double the atmospheric CO2. So any problems and effects we're seeing now, sort of saying colloquially, we ain't seen nothing yet. It's going to make ocean acidification forcing research a lot easier, but also we have to realize that the implications are pretty severe. A second thing that I want to emphasize looking into the future is that we don't have crystal balls. We have something which is close to a crystal ball, which are models. And here I'm showing one model which many of you probably have seen. This is based on the IPCC reports where we have different trajectories. And the way I like to look at these is basically how well can we behave into the future by trying to constrain the atmospheric CO2 levels. And so RCP stands for Representative Concentration Pathways. It's basically an RCP 8.5 means that is a pathway where we'll have a radiative forcing of 8.5 watts per meter square per year. That means as little to me as to any of you, and so underneath it is basically the average global temperature increase that we'd expect from an RCP 8.5. And then there are different other scenarios, and they used to call RCP 8.5 business as usual. If we just continue happily burning fossil fuels, we will be on this particular trajectory. All the other trajectories will require some mitigation. But the point of this plot in this context of ocean acidification is that when we look in the future, there is a lot of uncertainty depending what kind of model we use. And so the solid lines are the best guesses. All the little thin lines are different projections based on different models, and it has a lot to do that we don't really know the radiative forcing CO2 connection real well. It's also worth noting is that we are still happily going on the business as usual scenario at RCP 8.5. You can see that the model started in 2005. In the last 10 years, we've been following this high fossil fuel burning scenario quite happily. Also, it means that if we want to get into start mitigation, we have to get pretty serious to fall on these other lines. But now let's get back to ocean acidification. It is, if we look at the graph on the left, which is the graph which was shown in a larger scale in the previous slide, and then we compare it to what models say about global surface pH change. Again, this is there are not quite as many models, but this is results from a coupled model in the comparison project where there are about a half a dozen models which are used to look at what global surface pH change will take place. And what we can see is that, at least based on these models, we know that if we know the atmospheric CO2 level, we will know what the surface water pH scenario is. Also, I think it's worth and so on the top we show pH. I didn't believe that we can know it that well with models, and so in the bottom I show oxygen, and it shows that models have a bit more difficulty predicting, or they have differences in the different models for oxygen. For the pH, we don't see nearly as changes. But nonetheless, I think being somewhat of a cynic about models being a perfect predictor of the future, if you look at these models, both for oxygen and also for pH, is we know we can construct the future better than we can reconstruct the past, and I think that's a clear fallacy. So I think we want to take this somewhat with a grain of salt, but in first order, it is we have a pretty good handle, if we know what the atmospheric CO2 concentration is, what on global scale the ocean acidification will do. Also, sort of to keep in mind for the future slides when I'm going to the Secan region or this South Atlantic Bight, is that we are expecting a change in the next 10 years of about 25 microatmosphere in PCO2 surface water, since it follows this atmosphere quite well. which will basically decrease the pH by 0.026, change the carbonate ion by 10, and the aragonite saturation state by 0.16. So to keep those numbers in your mind, and these are based on a 10-year projection, and you can see what the variability is, compared to these projections. Also, it's worth remembering that different parts of the ocean have a different impact of increasing CO2 levels. And this is, again, this model ensemble from a paper from Laurent Bob et al. And on the top panel, we show they show the global average ocean where they switch from the pH to carbonate ion, which is on the left-hand scale. I've loosely, converted that to aragonite saturation state on the right-hand side. So what we see in the global ocean is that our aragonite saturation states stay well above this chemical threshold of 1. When we look at higher latitudes, we see that we, like the Arctic and the Southern Ocean, which are the bottom two panels, we see that within our lifetimes we will go below the aragonite saturation state. And although the biology is going to be impacted a lot earlier than that, we know that we are in a heap of trouble when we get below saturation state of 1. So in the current projections, and it shows on the different lines are the different representative concentration profiles, and it's the RCP 8.5, the business as usual scenario, is the red line and has the most dire consequences. Now let's get to that was sort of a very long introduction on ocean acidification and the future. Now let's get to looking at delving down a bit to the east coast of the U.S. and the Gulf of Mexico. What I'm showing here is based on the cruise, the GOMEC cruise, two cruises that we did a couple of years ago. The saturation states based on these transects on the left-hand side at the surface and on the right-hand side at 100 meters. And so there are a couple of things worth noting is that the further north you go, the lower the saturation states of aragonite. It is not a sort of a regular pattern. It varies some. And I'll explain to you a bit why we see sort of this this stream of low saturation state water sort of hugging the coast. Also, it is worth comparing the left-hand panel at the aragonite saturation state at the surface versus the aragonite saturation state at depth. And basically what we see is that the deeper you go into the water column, the lower the saturation states. And so most biology is at the surface, but still this water which is at 100 meters depth will have a significant impact on the surface concentrations due to mixing and upwelling. And so the numbers is that the aragonite saturation states in this GOMEC realm range from 2 in the north to 4.5 in the Gulf of Mexico. But when we dropped 200 meters, we see that the saturation states drop by about 1 when we just go slightly below the mix layer. We can delve into a bit further looking at cross-sections, and here we're getting a bit closer to the South Atlantic Bight region, which is the area of interest for SICAN. And what I'm doing here is I'm showing on the top sort of the northern boundary, slightly north of the northern boundary of the South Atlantic Bight, and the southern transect is just south of the boundary of the South Atlantic Bight. And so that's the panel on the right shows, and the panel on the left shows the cross sections of aragonite saturation state. And the scales are different. Every line during GOMEC has a name, and the top line is called the Cape Hatteras line, where we went into ocean waters which were over 3,000 meters deep. The middle panel is the creatively named the Georgia line, where we didn't get off the ocean margin. And then the bottom is the 27 North line, which is basically covering the Florida current. And what we can see is that you see a dramatic decrease in saturation states, particularly in the north. There you basically go from levels which are over 4 in the surface to undersaturated at depth. Also, what we can see for all these three lines is that the saturation state isoplasts are showing towards the coast. And this is basically a dynamic region, and this has a large impact on the coastal saturation states. Some of this water will actually get onto the shelf area. And it also starts illustrating that in the bottom is, if we know our basic hydrography, is that the Gulf Stream Florida current, which squeezes between the Bahamas and the east coast of Florida, you would basically have a fairly narrow channel of water which is going northward, going along the shelf. And this water is really interesting in that we always think of the Gulf Stream as a homogeneous water mass. From a saturation state perspective, it definitely is not. We have very, very low saturation state waters on the western side of the Gulf Stream, which again impacts the South Atlantic Bight. And we can see that evidence in the middle panel. You see this very low water is sort of creeping up the coast, and this is water of South Atlantic origin. If we blow up, this is again the same cross section, but as opposed to going to the full water column, we are looking at the top 200 meters. This is sort of the interest, where you have the biologic productivity, and it kind of blows things up. In the top, we have the Cape Hatteras line, where we see high saturation states offshore. When we get inshore, very low saturation states, and then this very strong front of very low saturation state water, which is basically hugging the margin. The Georgia line, we don't quite see it quite as prevalent, but we see the same issue that we have lower saturation state waters, which seem to be wanting to creep up into the coastal areas. And then on the bottom, we have the Florida current cross-section for the top 100 meters. And again, we see this very low saturation state water, which is basically hugging the coast going northward. This gave you a quick overview of the spatial patterns, large-scale spatial patterns in the South Atlantic Bight. Now let's look at the temporal trends. For the temporal trends, we are very fortunate that we have a mooring on Gray's Reef, which for the last 10 years has been taking CO2 data, and as I showed earlier, is that CO2 is very closely related to pH and saturation state. And so the full record, which is basically the mooring, is maintained by collaboration of investigators at PMEL at University of Georgia and University of Delaware. We see the PCO2 from 2006 to 2014 on the bottom show the approximate location of the Gray Reef mooring, which is part of the National Data Buoy Center mooring array. And what I've done on the right-hand side is I've just picked 1 year of data and looked at the sort of ocean acidification and its drivers. So what this is for year 2011, and since it was not a nice clean year, it basically starts in 2010, but it's about almost a full year of uninterrupted data. On the top, we see this big temperature change from winter to summer. You have about a 20-degree range in temperature. The salinity is a very important parameter within ocean acidification research. We see it's very, very blotchy, and this is one of the issues that we will have to deal with ocean acidification, is that continental influences have, which are often shown by low salinity waters, can have a very big effect on ocean acidification. Then we have, so these are, and then the third panel is the partial pressure of CO2. So these are the first three panels are measured parameters. And then since I showed earlier on that PCO2 and saturation state are fairly closely related, and I basically used a rough salinity-alkalinity relationship and got a proxy of the saturation state for aragonite. And what I want to drive home with this picture is that we see a large annual change and also subannual changes in aragonite saturation state, which will impact the ocean biota. So you basically have the changes on the shelf, range from about 2.4 to 3.6 in saturation state, which is as large as a change which we see from Florida to New England or from surface to surface. So basically, variability of saturation states are critical. And also, it is, most biota don't have a choice, and they will have to live through these big excursions. So it's not, biota does not see climatology, they see actual events. Now, a second means that we are looking at ocean acidification or saturation states in surface water is using ship of opportunities, where we basically have automated instruments on different ships, and so we basically able to span sort of the spatial temporal domain within the for the surface waters. As part of the ocean acidification program, we have two other NOAA fisheries ships outfitted with ocean acidification measuring devices, in particular partial pressure of CO2. And this is an older graph, but it looks like, for some reason we don't like the South Atlantic Bight. Part is that one of the fishery ships is primarily in the Gulf of Mexico. It's the Gunter, and one is in the Northeast, which is the Bigelow. And then on the right-hand side, what we're also doing is we have a community effort together where we basically are combining all surface water PCO2 data, which can be used for ocean acidification, in one global database, and this effort is called SOCAT. And so on the right-hand side, it shows basically the data that we have from Ship of Opportunity. And this is, although it looks kind of impressive with all these lines, these are basically all the ship lines where we have PCO2 measurements. This is over the last 15 years, and if you start breaking it down per season or per year, it gets very, very sparse. And this is despite the issue that we have major ports in the southeast with ships going in and out. But it's one of the things that getting more data in the region is going to be a fairly critical issue. Nonetheless, we have some very nice example of some data which I'm showing, which is a very nice paper by Rik Wanninkhof, published in 2010, to give you some idea of what we can do with these surface water observations from ships. These were small research cruises done over several years, which gives us an idea of the seasonal cycle in a larger domain than just at a mooring. This plot basically shows the aragonite saturation states for 6 different monthly representations, and the cruise tracks are on the lane. And basically what you can see is that there is a very large gradient from shore to shelf. So most of the work that I've shown before stays, out of sort of 10 kilometers from shore. We see a lot of changes, and I'm sure you'll get some really good presentations on the changes near shore. But I think the take-home message is that your gradient from shore to open ocean in this region can be as large as 2. What Rik and colleagues also did is they provided did some cross sections, and this gives you some idea of 3 different representations off the shelf in the South Atlantic, Bight, on the shelf and off the shelf. And we see, particularly off shelf, this influence of the large-scale current structure and water masses. And we see big changes. It's labeled versus month. I am not convinced that this is a seasonal change. These are interannual changes, which we'll get to in a minute. So talking about changes, we did 2 cruises as part of the GOMEC campaign, one in 2007 and one in 2012, and this, of course, gives you a great, possibility to compare them. And so this is the difference between the GOMEC 2 cruise in 2012 and GOMEC 1 in 2007. And again, this is saturation states at the surface. And what you have to remember is that we expect over the 5 years about a change of less than 0.1 in aragonite saturation state due to ocean acidification itself. And what you can see is this scale goes to minus 0.6 to 0.8. And this is sort of, when we sort of first looked at this, I said, oh, wow, we have some other issues going on. And so in a nutshell, what is happening is we saw over this 5 years is that the Gulf of Mexico got the acidification state dropped as a rock over, specifically near the coast. In New England, I think it's probably because they had a NECAN effort going, they managed to improve the saturation state by almost a half a unit. I'm being facetious here, but it is. But I think the big take-home message from this is that we see large changes over a fairly short time span, which are not directly related to sort of the pure definition of ocean acidification. We also could see, put it in context, we also saw between these 2 summers, the 2012 had the warmest sea surface temperature on record in New England. And we basically see the sea surface temperature, which is the top panel on the right, that the Gulf of Mexico was appreciably colder during 2012 compared to 2007, while the opposite was in the high latitudes. But it's not just temperature that is changing. We see a big change in salinity, where the northeast region got a lot saltier. We see also a huge, like to expect, a huge change in PCO2. And then we also can look at the aragonite saturation state, which is the bottom panel to the right. And we can, if we look at the anti-correlation between PCO2 and aragonite saturation states, we can see, how the PCO2 is driving the saturation state for large regions. It's also worth noting is that while the Gulf of Mexico was too cold, the northeast was too warm, the South Atlantic Bight was just about right. So this is a plot of differences at aragonite saturation state of 100 meters, so below the mixed layer, with a lot of arrows. And this is not dogma, but this is what we believe is happening between these 2 cruises, showing the influence of large-scale circulation changes. The blue arrows are what are the major conduits of water mass movement in the area, where let's start with, and the red arrows are what the water mass movements were, or currents were, in the first cruise in 2007. So basically, let me look at 2007. We had a loop current which went very close, very well into the Gulf of Mexico. There is independent evidence that this caused a very strong entrainment of waters from the Mississippi outflow system along the West Florida shelf. And then basically what we saw is we had these waters were entrained into the Gulf Stream system, and then at the northern part we have basically a northward, southward flow coming from higher latitudes, and it's mostly going over the float. Is this sort of the Labrador coastal current, which was in 2007 relatively well developed. Now in 2012, we know from satellite observations and from measurements that the loop current did not extend into the northern Gulf of Mexico. It sort of bypassed it and went basically up the coast. We also know that the Labrador shelf current was much, much weaker. So basically what you have is you have this dynamics between in the north between the southward flowing Labrador current, which has a very low saturation state, and the northward flowing Gulf Stream, which is a very high saturation state, which has a determining influence on the northeast. In the Gulf of Mexico, the effect of the position of the loop current, which basically goes from the surface down to well below 1,000 meters, has a determining influence on the Gulf of Mexico. These effects, again, don't have a primary influence on the saturation states in the South Atlantic Bight, but we do see small effects from this sort of seesawing of the current patterns. Now let's look at the Georgia line in the smack dab in the middle of the South Atlantic Bight, and look at some of the data we got between the two cruises. And I was very, again, I'm somebody who likes good measurements, and I was very impressed with the data when I plotted up this recently. So we basically are looking at 3 different stations versus depth, and the station locations are roughly drawn by arrows. And so basically what we see is that we have we see in the surface waters, we see a small but perceptible increase in aragonite saturation state for surface waters extending from the near shore off the coast at a level which we'd expect caused by ocean acidification due to anthropogenic CO2 input. Also what we see, in particular in the middle panel, is that we see big changes due to water masses which are basically on the in the margin system, where we see while we expect increases in the surface and not big changes subsurface, we do see these appreciable, particularly in the middle plot. So just we are close to wrapping it up. If we look at it, we expect changes, which I showed in saturation state of in the next 10 years of about 0.2. We basically have to try to, if we can measure this, I think it's a very important take-home message, but we have to basically look at these changes in a context of large-scale regional and temporal changes, which are, which basically can confound, 3 decades or 5 decades worth of changes due to anthropogenic CO2 input. Looking into the future, this is again the work from the paper in Yang et al. We can project forward, and what I just want to sort of highlight here is it's a representative seasonal cycle, and we can see in the springtime and wintertime that the saturation states in the South Atlantic Bight will drop below this threshold that Ekstrom used in its vulnerability index of below 1.5, while the paper suggested that this wouldn't happen until after 2100. This is sort of a example, and what I've basically done is, while the Ekstrom and colleagues felt that saturation states would not reach this critical threshold, they used 1.5. I believe that, based on the data we know so far, is that we probably will reach the threshold, at least for certain times of the year, and which will have significant socioeconomic impacts in the region, which is already very sensitive to these social and economic issues. So in summary, the ocean acidification is real. It's here to stay. The trends of ocean acidification can be determined on 5 to 10 year timescales. The challenge is to separate the ocean acidification effects from other effects, and I think we have a lot of tools and measurements to do so. For the South Atlantic bight, the far-field influences and feedbacks on saturation state need to be considered, and changing ocean currents have a first-order effect on the saturation state in this realm. So, as a closing remark, getting back to the Best of Raw Foods website, I would say step 7, if you go through that website, is get healthy, get alkaline. I guess that's a good sort of exclamation point for our oceanification research. And also eat more seaweed and superfoods. So thank you.
Thank you very much, Rick. I really appreciate such an informative presentation, especially for the first day of science. I think you've really set the stage for follow-on webinars. We do have one question coming in. You mentioned that we will reach the threshold earlier than 2100. Can you give a projected date? I think, or you may have missed the dates, or mentioned the dates and they were missed. Can you repeat those dates if you mentioned them?
Okay. No, I did not. Give a date. It would be, yes, sort of doing a linear interpolation. It would be, I would say, about 50 years from now, as opposed to 80 years, 90 years.
Thank you. Okay, are there any other questions? Okay, I'm not seeing any other questions. Let me just check one more time. Okay, here's another question from Deborah. What are the other major things that will impact saturation state in the South Atlantic bight?
Yeah, that's a very good question, and I expect that most of the other presentations where they're talking about chemical forcing will address this. And the really important issue, which we saw in the Yang et al. Paper, is the influence of coastal runoff. So coastal runoff is extremely important to the ocean acidification patterns. You basically have, fresh water which is not very well buffered, which is, fairly acidic, which is, coming through the marsh system that is going to be impacted. So it's mostly the coastal runoff. I think one of the things that we are, not paying full attention to is actually precipitation as well. It's an area where we have significant rainfall events which can, really change the saturation states appreciably.
Okay, thank you for that response. Are there any other questions? If you have questions, please type them into the question box on the sidebar. Okay, I don't see any, but while we're waiting for maybe one or two to come in, if you think of any questions and before we close, you can send them to Rick, and you can contact Rick on the information on that was on the webinar. And if you are interested in joining the SOCAN listserv to learn more about future updates in the Acidification Network, you can sign in at the first link that you see on this particular slide. And we'd like to thank you for attending the SOCAN State of the Science webinar today. We welcome any feedback or further questions or suggestions for topics that you have for upcoming webinar series, and you can submit input by replying to the follow-up email you'll be receiving or emailing us at the email listed on the slide here, the second one at abby@socorro.org. Next week, we will be hearing about estuarine acidification, a conceptual discussion with examples, and that will be presented by Wei-Jun Kai at the University of Delaware. That will be on Wednesday, March 18th at 12 o'clock Eastern Standard Time, and you can see the link below for registration information. So, Rick, I'd like to thank you again for an exceptional presentation on ocean acidification and coastal acidification in the South Atlantic bight. Thank you very much. And thank you all for attending. We look forward to seeing you for our next SOCAN webinar.